So we're going to start our journey into Postgres and SQL today. I know folks have seen a little bit of it during Full Stack Week and possibly during Foundations of Programming. Today we're going to do a deeper dive. Today we're going to focus on the basics of schema design, or sort of designing a database, and some best practices, including a concept called normalization, using primary keys, which I think we've all seen a little bit, creating indexes, which we haven't really talked about. I'm going to talk about sort of the standard Postgres column types. And then we're going to do a little bit of practicing of some different schema design sort of scenarios. And then in part two of the lecture, we'll get a bit more hands-on. We'll talk a bit about the difference between psql and Postgres. Excuse me. And then we'll actually make a Postgres database, make some tables, use psql to do more and more stuff with Postgres, copy data from CSVs, and actually write some SQL scripts that we can run with psql in Postgres, so we don't have to type out everything manually. Does anyone have any questions about the agenda for today? Okay, awesome. Today is very much sort of like the foundational building blocks of databases and starting to think about designing our databases. Tomorrow, we will see what's called constraints, and where we can set more rules about our data. And that will delve a bit deeper into relationships between tables, though we will be talking about that today as well. In fact, I probably should have added that here. And then finally, Thursday, we'll actually talk about querying data, which I think is what we all sort of, that's my default image of like an SQL database, at least, where it's like select star from users to get the list of all the users. Can I get a quick volunteer, and could someone please just read me this first paragraph here at the top of our lesson doc?
Database schema design refers to the process of defining the structure that represents the organization of data in a database. A well-designed database schema is crucial for ensuring data integrity, performance, and ease of maintenance. Here are some good practices and potential pitfalls to consider when starting your database schema design.
Awesome. And thank you, Jack. Yeah, so schema is just a fancy word here for design. Think of it as, with Python, we have source code. With relational databases, we have the SQL that creates all of our different tables. And so when we talk about the database schema, you could think about it as all the SQL to create all the tables and all the relationships and all of their rules. There is this sort of concept in like data modeling or data design of, let's actually see if I can find it in our curriculum, because there's a nice diagram floating around here. So we're not going to dive into, there's a whole process that I learned in school called entity relationship diagramming. This is under optional lessons, by the way, if anyone wants to poke around in this stuff. It can be interesting. As you can see here, it's like a much more abstract way of thinking about a data model. It can be very useful. Some people love it. Some people don't like it. It is a bit heavyweight, and we kind of cut it in the interests of time. This is sort of how I learned to do it in school. It can go a bit over the top, as you can see here. But what I wanted to go to here that I think is useful to take away is when we talk about designing a database or a schema or a data model, there's kind of three levels that we can think about here. There's a conceptual level where we're not even thinking about tables and relationships and Postgres and SQL. We're thinking the business level in terms of business concepts, or the sort of feature level in terms of, all right, I've got a workout app, so I need a workout and a user can do a workout and there are different exercises and a workout, has to have at least one or more exercises. And we're thinking about the concepts. Um, a level below that is what's called the logical level that talks about the structure of our data. And this might be the SQL creating all of our tables. And then there's what's called the physical level. And the physical level, often we don't deal with directly. It might include things like indexes, which we'll talk about in a bit for optimization, something called B trees that we don't get into. Modern database engines like Postgres do an awful lot of stuff for us. And to some degree, the physical level could even be like how the data is stored on a hard drive, right? And so it kind of can vary what part belongs in what level here. So I don't want us to get too lost in the sauce, but I do want us to take away this idea of having like a conceptual model of like these things for whatever it is we're building. And then we start to figure out the logical model that connects to the database, right? Because just the same way that I might go into TLDraw to start drawing out my UI before I start writing React code, thinking a little bit at a higher level first can help us a ton. Does anyone have any questions about this sort of like distinction and this idea of these three layers?
I guess I have like a clarification
Yeah.
portion on like the conceptual part. Can you give like an example of like what a business concept could be?
Yeah, totally. So if we have, say, like a workout app, and we'll just call this like workout app, and I'm gonna get rid of this because we don't need it at the moment. Well, my workout app might have a user, right? Users can log in, and this, let's say, is for tracking workouts. So then a user can do a workout, and while a workout can be one or more exercises, and then I might start listing more stuff here, like a workout has a date and it has a time and it has, exercises. And an exercise might have type. Um, and maybe, do I want to deal with reps and sets? Like maybe do I want the exercise? Maybe this is just like type and I don't know, equipment. And so then maybe I need an idea of sets for my workout where there's an exercise, there's a number of reps, and then my workout, it's not actually exercises, it's sets. Right, where I as a user log in, I do a workout, my workout's got a date and a time, and what I keep track of is, all right, I did like 3 sets on the cable row because I'm slowly starting to learn stuff and working with the trainer. And so I've got over here in my exercises table, a cable row exercise and whatever information about it I want. But I also list here like the number of reps that I did and if I did like 2 or 3 sets on the cable row. So this is a conceptual data model, right? I haven't made any tables. I haven't written any SQL, but I'm talking about the application, the feature concepts or the business concepts for what I'm building. Does that help answer your question, Chase?
Yeah, it does. Thank you.
Yeah, great question. And as you all saw, I kind of like I came up with exercises and I was like, oh, wait, maybe we need sets because originally some of this was going to go in here. And there's a lot of different valid ways to design this, right? There's other ways just as good that we could design this instead. But it can be kind of nice to think about stuff at that level because it's so easy to change things. And I can think about it without worrying about like SQL or writing code or anything like that. And it also helps me figure out better like what my features of my app should be. So often, like if I'm designing a new application from scratch, like features and data model are some of the first things that happens, right? Because the features here are a user can sign up and a user can do a workout, and in a workout, the user can track the date and the time, and the user can track what they did in the workout, right? Those are all features. I, as a user, can say, like, for my workout yesterday, I did like 2 sets of 15 reps on the cable rope. And then how do I design a data model that'll help me like build and implement those features? And I just want to check in to see if folks have other questions around this or things that you're curious about. Oh, sorry about that. Cool. And let me actually pull up our questions channel here in Slack to make sure that I have it at the ready. If you all will just give me one moment.
So to be clear, features determine the type of essentially the data model or like the actual how the database will be structured.
Yeah, we're gonna it'll happen later when we do a product workshop with Judith, but the classic way to come up with features is something called user stories. And the easiest way to come up with a user story is to say like a user should be able to, and then just start making a long list, right? Sign up, log in, track their exercises in a workout. And then maybe I have to drill down here. Do I want a feature to track sets and reps? Yes, I do. And that's my decision as the person creating the program. Track sets, reps for each individual exercise. And, maybe like get a weekly like, report or weekly like dashboard view. Maybe that's another feature that I want. And so as I come up with features, just like we have to write code to implement it, we also want to start thinking about, well, what data do I need to save? And how do I want to organize that data? And then we kind of can start building our data model. But that's what we're going to practice today, which is schema design. We're going to get a lot of practice at this. Does that help answer your question, Kenny?
Yeah.
Awesome. So the good news here is this is a pretty like well understood problem, and there's a lot of good principles that we can follow along here to do this. And by the way, I recommend like don't worry too much about the distinction between like the conceptual data model and the logical data model. We're going to use this tool draw SQL a lot in this class. You don't need to make an account to use it, I don't think. It's also free. As you can see, I've been using it, but I haven't logged in since Victor Platoon. Oh, and there we go. And some people really like using this tool right off the bat, and it's great because it's visual, right? And we can come back to this later, actually, in fact, and we could build this out. Like you can start creating relationships, which we'll talk about in a little bit, between tables, and you can add columns and stuff. And, is this the logical data model and not conceptual? Yes, I guess so, but it's useful, right? So whether it's TL draw or draw SQL, I would say use the tool that helps you the most. For what it's worth, I think there is some value to, on a piece of paper or on TL draw, doing something like this before you bust out draw SQL. But at the end of the day, the goal here is to help you come up with a good design, and there are a lot of ways to skin that cat. So, good practices for schema design. I don't want to get too deep into this concept here called normalization. Essentially, the idea here is not to duplicate data. I don't want to have a ton of shared data in a bunch of tables. For instance, for my exercise type, let's give it, like a name, and this is going to be, I'll talk more about the data types in a little bit. But so this could be cable row, push-ups, sit-ups, so on and so forth. And let's see, let's put this over here and this over here. And let's say my workout, it's going to have a bunch of sets. Actually, the relationship between the sets and the workout gets a little tricky, so I think I'll come back to that later. But the set is going to have an exercise type, and maybe we make this a text field. And maybe I want to have, number of reps, and that's going to be an integer. And so then here I might end up with, 20 push-ups because I've been doing awesome and going to the gym. And then over here for the exercise type, I might have push-ups here too for the name of the exercise. So if I have this name push-ups in two places, that's kind of a pain, because if I need to change the name of it for some reason or modify stuff, I now have to do it in two places. It also makes it harder to keep our data organized. So sort of the core idea of normalization is reducing this duplication where, hey, you know what? Actually, and let me go ahead and clear this stuff from Zoom. This exercise type isn't going to be a bar chart at all. It's going to be an ID. We'll make this integer, and we'll connect it over here. Where this really shouldn't be. There we go. Where I'm not going to store the name of my exercise in two different places. I'm going to store it in one place over here in the exercise type table. And I just want to check in to see if that example makes sense to folks. And if people are tracking with what I'm saying. Yes, no, maybe. How are we feeling? Cool. Yeah. Basically, I'll draw it out real quick, and then we'll kind of move on. This is the other way I like to kind of, that I think is useful with this stuff. is call this and let's say that this was a table. I don't know why we have that empty column there, but that's okay. And let's say just for fun, we also have the workout table. Though that one's a little trickier, actually, so I won't talk about that now. But let's say each of these represents, a set of some exercise that I did in a workout. Well, if I design my database this way, where I enter the exercise name in two places, I've got duplicated data, right? And as we get tons of users, this might take up more space than we need. And also, if I need to change the name of this for some reason, I don't know, maybe I want to change it to be this or whatever, then this kind of becomes messy. Also, we might, maybe there's useful information that we have here. I don't know what the right word is. And maybe I want to be able to grab that information more easily. Well, instead of this, let's just hold an ID, like a variable name or a reference. And so now I've got here a set of 10 push-ups, a set of 10 sit-ups, a set of 10 cable rows, and another set of 5 push-ups. And so does this kind of help illustrate, as a practical example, like how we want to kind of avoid duplicating data when we're designing our data model?
Yeah, I
Awesome.
think that does pretty good.
Cool. Yeah, and I see a couple nods. And hopefully this should feel relatively straightforward, and it is. Excuse me. It is pretty straightforward. Normalization can get a little over the top. It actually, there's like 5 levels of normalization, I think. But this is the best starting point and sort of like the key concept. The other key concept of normalization is like each column should hold 1 bit of data that represents one thing. Like, I wouldn't want like this, where this column, say, if this was a string, holds 2 things, right? The number of the exercise, how many reps of my exercise I did, and the name of the exercise. Because the whole goal of like using a database is to make it really simple to work with and manipulate this data. So that's the other thing that is good to think about. Try to have like each column just represent one simple specific thing. And it's okay to have lots of little columns. The truth is that data storage is cheap, right? And so don't hesitate to have like lots of little columns for separate things. So that's normalization. Don't worry about going overkill on it. It's okay to have some duplication in the beginning. The next is primary keys. And I think we've all seen this idea. A primary key is a unique ID for a record. And we can see here in this draw SQL, it added this ID category. And let's say for my user here, I wanted to add another column for email. So a primary key needs to be unique per row, right? And if we were to go over here and we were to have a user table, and let's we'll give it some columns and rows. And every user gets an ID. They've got a name and an email. And let's say we have two Alices. We're not going to worry about last names at the moment. But, you know, they've got to have different emails. I can pretty much rely on an email to be unique. What are some advantages or disadvantages of using an email as a primary key for this user table, as opposed to, say, an ID that it auto increments where we just increase it every time we get a new user?
Advantages, it'd be easy to find that user very quickly without having to write complex code to sort through anything.
Yeah,
But
exactly.
disadvantages, a single typo in that process is going to screw you up.
Yeah, and I think you laid out the advantages really well. It's far easier to find a user with ID of 1 or 2 or 3. Also, as we go to hundreds of users and maybe or really thousands, and we have, let's say, dozens of tables with lots of relationships, it's a bit easier for the database to make those relationships if the primary key is a number, is an integer. The other thing is, what if Alice changes her email? Right, then that would cause us some problems if we're using emails to uniquely identify users in our database. There are certain situations where maybe you want to use something other than it, like an integer for a primary key, but almost all the time you just want to have an ID field, and that's your primary key. And Postgres, rather Django will in fact do this for us, and it does what's called auto incrementing. So it just has a little counter and it keeps track of the most recent user ID and just adds one and keeps on increasing. And, you know, if at some point Alice leaves and we have another user, that's totally fine. So primary key we use to uniquely identify a row in our table, a row of data, and we almost always want it to be an ID. And I just want to check in to see if folks are curious about anything around primary keys or have any questions. Cool. So this idea of foreign keys, right? We kind of saw this with our workout example. A foreign key is where we're going to use some other table's primary key to help establish relationships. And to go back to the draw SQL diagram here, in fact, I think we should add a key here we have a good example of a foreign key right here, this exercise type ID, where I did a set of 10 push-ups. Well, what exercise type is this 10 of something for? It's for push-ups. So this is a foreign key pointing to our exercise type table. And in fact, over here, we should add a column and we should call it user ID. And we're going to make it, it's not actually a unique key, but I am going to drag, I'm going to kind of redo this. So this workout table has a user ID column, and that holds the ID of the user that did the workout. And I might have 5 or 10 workouts if I've just started using the app and I'm working out once or twice a week or something. And to kind of go to, and let's put this here and also grab our spreadsheet here. To build this out a bit, and let's just stick Carol there and we'll make her 2. Actually, excuse me, it's not the user I need to modify. It's the, I need to add a workout table. So let's do that right here. Where maybe I have a workout. So not a trick question. Who did these workouts?
Carol,
Yeah, exactly. And why Carol, Jack?
because her user ID is equal to 2.
Yeah, exactly. And thank you for answering. I know it's almost like a rhetorical question, but just getting, I think, some other people talking makes it a little more engaging. So this is a perfect example of a foreign key, right? Where this user ID column is explicitly designed for us to like refer back to this other table. And we see the same thing here with exercise ID. And when you're naming foreign key tables, I recommend naming them like this. It's the name of the table we're referring to underscore ID because it's simple and consistent. And we will actually be able to tell Postgres what these relationships are, and it will keep track of them for us, which will make querying so much easier. And Postgres will also enforce certain rules so that, say, like, we probably never want a set to be created without an exercise. And this is what's called data integrity, right? This wouldn't be very useful if I had a set of 20 reps, but I don't know what the exercise is. And we'll learn more about that in constraints tomorrow. But when we set up these relationships, that's one thing that Postgres as a relational database will do for us. So I just want to check in and see if folks have kind of any questions around this foreign key concept and the example here.
I have a question.
Yeah.
Were these, like, for example, the workout table you created with the user ID is all 2? Is that going to be a massive table in reality, or are there individual tables created dynamically per user?
It would be one table with a whole bunch of rows.
So a whole bunch of rows for different users. So in reality, you'd have user 2 and 4 and 7, 9, etc. all tracking their workouts through that same table.
Yep, exactly.
Okay.
Exactly.
And then you just sort it by lookups, or you
Exactly.
retrieve data by lookups. Okay.
Yeah.
Thank you.
Yeah, great question. Yeah, and you touched on a really good point. Um, Storage is cheap and database engines are really efficient. We can have thousands, frankly, tens of thousands of rows in this workout table, no problem. And if you think about what the data is, an integer, another integer, and a date also represented as an integer, it takes up so little space. Frankly, even text doesn't take up a lot of space. And in a minute, we'll talk about how you can set rules for like how many characters this can be. Now, this is another reason why normalization is good, because for this workout, if I had like a whole bunch of columns for each workout that said like push-ups and sit-ups and cable rows, then, having like 10,000 rows in my workouts table might become a bit of a problem. But because we're not duplicating information, it becomes really easy to do that. And Postgres and other relational databases like MySQL are really, really good at filtering, just like you were saying, Tim. So like writing queries is going to be really efficient to find all of Carol's workouts in this table. I think you all have probably seen some SQL like this. Um, right? Let's get all the rows and all the columns for each of those rows from the workout table where the user ID is to. And relational databases are incredibly good at doing these queries efficiently. Yeah, great question, Tim. And this is a good one to dig into because foreign keys are probably the most important concept to get comfortable with here. So what other questions do folks have around foreign keys? Okay, awesome. So don't hesitate to make foreign keys. Also, by the way, it's okay to have tables have lots of columns. There's nothing wrong with that either. There's more than one way to skin a cat here. We'll learn more about cascading actions later, such as I don't want to delete a user that has workouts, or if I want to delete a user at all. We'll talk about constraints later. We'll learn about them tomorrow. There's all sorts of rules that we can have, like that a column can't be null or that each value might be unique. For now, the only thing we have to know is that primary keys have some built-in constraints. A primary key has to be unique. So to go back to my example here, Postgres would throw an error if we tried to do this and adding David to the users table because this ID primary key is not unique. We wouldn't even be able to do it because Postgres, in fact, creates the ID for us. That helps ensure our data integrity, or what's called referential integrity, so that I can always easily find someone by their primary key. So for example, this also would cause a problem. Squats. Because this primary key is the same as this one here.
Um, I guess one thing I did notice early on, I guess like when we did SQL before, like, if you take away a value, let's just say like a user quits, but then gets added, but then you add a new user,
Yep.
the primary keys get jacked up. So it'll go from like 5 to 7 or whatever. I mean, I
Yep.
guess you can rewrite it so that doesn't happen.
Even better, we don't have to worry about it. It's totally okay for the primary keys to get jacked up.
As
Like
long as they're
we
unique.
have, if we do add David here as a user, and we've deleted Bob, this is okay. Some of you might, in fact, have run into this with the Pokemon API. I'm not sure all those primary keys are sequential, though most of them are. We're not guaranteed that primary keys will be always like that, there won't be any gaps. Right? We can probably infer from a primary key if a user joined like sooner or later, but really we shouldn't rely on the primary key for that. If I wanted to say no when a user joined, I should add a join date column here and have a date. Because sometimes when we do data migrations or other things, maybe a primary key will change, but also sort of following the principle of single responsibility and having each column be like atomic or do one thing. It's better for us not to try and infer too much from one column of data. So it's okay for the primary keys to have gaps like that. Yeah, great question. What else is on people's minds? Cool. So we were talking about data types. Oh, I did want to point out with foreign keys, by the way. And in fact, to kind of build on this example a little bit, let me kind of move all this over just a bit, just a touch. And I'm going to move this over just a touch because we're also going to add here maybe a user ID. Or it might in fact be
Thank you, though.
a
Kenny, you're
workout.
hot mic'd.
Oh, and I think someone has a hot mic. So in this example here with this sets table, I've actually got two foreign keys. I've got an exercise ID that tells me like what the exercise type was. And I've got a workout ID that tells me what workout this set was for. And note that if I want to figure out what user this set is for, I kind of have to jump through a little bit of a hoop here. And maybe this is okay, or maybe I want to simplify the design, though this is nice because I can track all the sets in a workout and have that connected to a user, but it has added an extra step. So if I look here, I see that Alice, or excuse me, Carol with an ID of 2 has done a whole bunch of workouts. And this workout ID of 1, if I look over here at these sets, I see all of these belong to Carol's workout on the 12th. And then I can see the individual exercises. And here, like these don't have to be unique, these foreign keys, right? I want duplicates to be here because that's one of my features. I want one user to be able to have many workouts. I want one workout to be able to have many sets in it, including maybe even like multiples of the same kind of set. And I want a set to be able to have like different workout IDs. I just want to pause and check in and see if this makes sense to folks. I realize I've done a lot of kind of messy drawing here. And do folks kind of see the relationship that I'm pointing out here with this workout ID property and the user ID and workouts?
It makes sense. But if data is so cheap and the data types are so small in size,
Mhm.
what's the benefit of having so many additional tables instead of one massive table where you just use selective queries It's like instead of select all from workout where ID is 2, say select exercise from workout where ID is 2 and date is this.
Yeah. Um, which tables are you proposing combining again?
All of them.
All of them. Right. So it's like,
Because they're all interconnected. Each table is going to be primarily composed of user foreign keys from other tables from which they need to take data in order to efficiently actually use the database, right? So
right,
what's the advantage of having multiple tables broken up if the foreign keys are so pronounced in between all the tables?
right. Great question. Great question. And sometimes the truth is it's okay to have one giant table and a bunch of duplication because storage is cheap. Um, part of this is for learning purposes. And the reality is, as cheap as storage is, if we have to start dealing with stuff at scale, it still matters. Think about the payroll database for Walmart or the IRS or all the users on Netflix and their playlists or all the users on Spotify and their playlists. Once we get into, the millions, then as cheap as storage is, it still matters.
But
Um,
wouldn't it be cheaper to have one database or one table instead of multiple tables because each table in memory has to be, or in storage has to be uniquely hashed to identify that as a separate table, which takes up additional space?
Short answer is no. Creating tables is genuinely a cheap operation and not what's going to eat up storage, because that's what the database engine is designed to do. Um,
So I'm still failing to see the advantage.
yeah, I would say so. There is a way to do what you're talking about. It in fact uses a different kind of database called a NoSQL database that's more like a big JSON object, and you just stick stuff in it. Um, Here, I would say the advantage is, let's take exercise type, for example, like push-ups, sit-ups, cable rows, squats, right? Um, for one thing, what happens if we decide we need to change the name of an exercise and I don't have the name kind of uniquely here if I have it spread out over a bunch of rows here in sets, then that becomes very difficult to change. Also, what if I want to give the user a list of all the different exercises as they're entering data into their workout? It could be nice to have all this information here on its own for other feature related reasons like that. Also, I might have a lot of additional information here about these exercises. Like maybe I have, like, I don't know, number of calories burned per exercise. Maybe I have a link to an image file or a link to a video file showing how to do a push-up. I might have a whole bunch of extra information here, right? That I don't want to necessarily just have spammed all over the place. Um, Similarly, with users, we might have additional user profile information where I don't need the user's email and their profile in every single workout. I think those are probably the most kind of immediate things I would say. I don't know if that helps illustrate it at all, Tim.
It does actually perfectly. You answered my question. Thank you.
Yeah, for sure. Yeah, and you're on the right track thinking about this stuff. As we'll see, like creating tables is actually really cheap. A lot of this is about organization. Um, and these tables like often serve like multiple functions. Like for example, here with the workout table, like combining workout and sets in this example, I think is something, where there's a good discussion of trade-offs to be had. And there's maybe like a simpler answer. Um, and I don't want to get into it now, but in fact, using a non-relational database, what's called a NoSQL database for, say, Twitter or Facebook for social media is where it's really popular, sort of it follows the approach that you're talking about, Tim. So we've kind of gone through a lot of these practices. Um, Indexes, I'll just talk about, I'll talk about data types. in a moment. I think I'll just cover these three because they're a bit briefer. So indexes, we can create these manually. We don't need to worry about them too much. An index basically is a way of telling the database, hey, I'm going to be looking stuff up by this column a lot. Like say, select star from user where email equals david@gmail.com. We might be doing that a lot, right? When users log in. So I might want to tell Postgres, create an index to do some hashing or some other clever stuff so that I can look up stuff in this email column faster. And we can actually manually tell Postgres to do that. I would not worry about that too much right now. Postgres also automatically creates indexes for primary keys and I believe for foreign keys as well. So it does some of that for us. Consistent naming conventions, name everything lowercase, follow a consistent naming convention, use underscore, don't use slashes, don't use spaces, don't use special characters. They can come back to bite you. And I always have to double check, but SQL table naming, singular versus plural. And as you can see, there's like a lot of discussion around this. Should it be customer or customers? Should it be user or users? To be honest, I try to go with singular, but I forget. I think the important thing is just try to be consistent. I'm not consistent here. Like this should be set. Go with whatever is easier for you, but just be consistent. And in fact, it will make your code a lot easier to work with. Documentation. Postgres takes care of a lot of this for us because it can actually print out the SQL schema. The biggest thing here is draw diagrams. Don't hesitate to use draw SQL or TLDraw. And like if you're using SQL to modify your data schema, save the SQL you run in a file. But as we've seen, as we're going to see, Postgres actually does a lot of this for us. So these are some bad practices. I'll just run through these briefly. Just keep these in the back of your mind. This is basically premature optimization. Start out simple and you can worry about reducing duplication and other things later. Ignoring indexing, maybe it's a bad practice. To be honest, I wouldn't worry too much about indexing now. Get your data model working. Once you've written a bunch of queries, so you actually can see how you're using the database, then you can think about indices. We'll talk more about this tomorrow in constraints and relationships, but this is a bad practice. We kind of want to set as many rules as we can. This one is important. The whole point of a relational database is to have relationships between tables because it lets us leverage the power of SQL and Postgres. Inconsistent naming is always a bad practice. And these others are sort of more general design principles. So we're coming up on the hour. We've talked through a lot of these fields. I think what I want to do is, why don't we take a 10-minute break? And then I will quickly walk through with Draw SQL some of the different field types we get with Postgres. And then what we can do actually is maybe like, we'll walk a little bit through relationships, though we've done a good amount of that. And then what we'll do is we'll walk through one design scenario together, and then you all will have about 30 minutes to work on another design scenario independently. Sound good? Awesome. Thank you very much, everyone, and I'll see you all in 10. Let me go ahead and pause the recording. All right, so just to recap, we've covered a lot about sort of design principles. If I hop back over to here, we talked a little bit about normalization, which is basically reducing or getting rid of duplication in our data model. We talked about sort of the conceptual versus the logical data model. We've talked about primary keys and indices. We saw a little bit about relationships, building the workout app. We're going to kind of go through them in full in a moment. And we saw a couple column types, but I'm about to walk through those now. I also do recommend, by the way, I do think just busting out a spreadsheet sometimes is helpful. What it can actually be really helpful for is when you're trying to figure out how to write a query. Sometimes it's easy to just kind of highlight stuff to figure out what this SQL query should look like. Let's talk a little bit about data types, and then we will go on and talk about relationships, and then we'll sort of design a data model together, and then you all will work on one independently for a bit. Sound good? Cool. So, first off, the Postgres docs are incredible. They go through everything. They are easy to read, though a bit dense. If you are looking for something extra to do, I actually highly recommend this tutorial they have. You can kind of skip ahead, and I would start here maybe with like the SQL language and creating a new table where it walks through everything step by step. It has a pretty amazing set of explanations about stuff. Again, it's in depth, but quite approachable. The tutorial will probably take you some time, but you'll learn a ton. I also recommend just going straight to the docs as you're figuring stuff out, because it does do a very good job of explaining things. Like, for example, when they talk about how to write a query for a table, and more relevantly for us with data types. And if we scroll, and you can see they go through all the syntax of SQL, all these other things. And if we go all the way down, we should get to Postgres data types. Let's see where they are hiding it. There we go, data types. SQL, by the way, there is a common standard, though there's what's referred to as different flavors. So like 90% of what you're learning here will work just fine with other relational databases such as Microsoft SQL or MySQL, though each one is a little different. And as you can see, Postgres has like a really rich breakdown of all the different types. It has a ton of different types, by the way. Like it has types for geometry, specifically for points and lines and boxes and paths. A bit less relevant to us, network address types. What actually is kind of cool for your personal project, it actually has a JSON type. If you want to just stick a whole bunch of JSON in a column, you can, and you can actually search through that JSON. And as you can see, there's a lot of reading here, and this kind of borrows from that NoSQL database. Much more relevant for us is text types. Which is hiding somewhere around here. Let's see if I can find it. As you can see, I'm getting a little lost in the docs at the moment. It's got to be kind of in front of my face, and I'm not seeing it. So I'll just demo it here in Draw SQL. So there's two main types for text, varchar and text. Varchar, say here for the user, we can say how many characters I want it to be. So I could say, hey, this varchar field can't have more than 20 characters. And that can be useful if, we're Spotify or something like that. Or if I want to like have sensible data, like maybe, an email address shouldn't have more than 20 characters. By default, a varchar is limited to 255 characters. A first name maybe shouldn't have more than 20 characters. I wouldn't worry too much about adding like the lower limits on varchar. You can if you want. It is good to think about. The text field is for like sentences and paragraphs. So for a workout, maybe I want the user to be able to add, some notes. And that should be a text field type. And so this could be several paragraphs or larger. And somewhere in the Postgres docs, it does break down the different text data types. For some reason, I'm just having a hard time seeing it here, though I know it has to be there and it's probably right in front of my face. For primary keys, Postgres will do what's called a serial field, where it automatically increments the value for us and it handles it. And that's by far the easiest type to use and what we should stick with. And as the docs tell us here, they're not real types, but they're just a nice convenience for creating unique ID columns, often called auto increment. And it's an integer under the hood, but in fact, Postgres is doing a bit more. There's something called a sequence that it can create. That is how it does the auto incrementing. And it adds a bunch of rules. We'll talk about these constraints tomorrow, not null and default. And it kind of sets the next value. So this is peeking under the hood a bit for what Postgres is doing. But the good news here for us is this is super easy to use because, well, it's a little hard to see here in draw SQL because we just call it big int. But once we've identified this column as a primary key, Postgres will take care of that for us and do the auto incrementing and everything. For the numeric fields, there's really only two things we have to think about if we need an integer or a decimal value. If we hop over to the docs here, we can actually see they break it down quite well. They have a number of different integer types. Small int, integer, big int, which again, if we have millions of users or tons and tons of data, then maybe this begins to matter for space efficiency and storage. For us, honestly, we should just use big int to start with because it's usually simpler and things do get bigger than you expect, though this is an awfully big number. But in the real world, you'd be surprised how quickly you might pass this small int upper bound of 32,767. Right? Maybe, if we're designing a program to keep track of lockers for schools and student lockers, we could use, maybe we could use small int for the locker number, right? But what if we decide we want to make our locker ID numbers longer for some reason or add an extra zero? Or what if the program becomes used by multiple schools? That's a bit of a contrived example, but in general, you can just stick with big int. It's good to know these are there. Decimal and numeric are what matter more for us for when we need floating point numbers or decimal values. These two are, in fact, basically the same. I think decimal is a placeholder for numeric. In fact, if we scroll down a bit in the docs to look for decimal, it's hiding somewhere in there, but I believe the docs actually tell us that decimal is just a placeholder for the numeric type. What we can do both with decimal and numeric is give a precision and a scale. So I can say how many decimal places I want this number to be to. And I would do it like this. If I can hop over to the right one. And maybe for sets, we want calories burned, and it's going to be decimal to with maybe we want to only like 2 decimal values of precision, or even only one, like 4.5 calories seems about right for calories burned. If you're working with financial data, that's when specifying precision becomes important. Though often with financial data, you actually store the value in cents. Postgres also offers really good values for date and time. And by the way, with the numbers, I do recommend just spending a little time reading through these. We kind of have a summary here, but it's worth doing a little bit of reading and skimming through the numeric types as well. And let's go back up to data types. It actually, Postgres does have different types for money if you have to deal with money, but date and time is really what's next for us and what's interesting. As you can see, they've got a bunch of stuff here. They have a timestamp without time zone, a timestamp with time zone, a date value, and also a time value. There's also an interval. So we could have 30 minutes for our workout app. Say, maybe we had a column, minutes spent. And this is where draw SQL, I think, reaches some limitations because it doesn't actually have the interval data type that Postgres does. Which is a little annoying. But so for our workout, we probably want a date. Maybe we don't need a time. Maybe we do. That would really depend on our own decision about how we wanted to design our app and what features were important. So then I probably want a date and a time. You do have to be a little careful with time zones to think about the time zone of the server. You usually want to get the time zone from the user, because if I'm on a plane trip to Florida but I live in Chicago, my default time zone, if I loaded that into the app, isn't going to be good. And if the server is running on a server in like Virginia on East Coast time, then we need to be a little bit careful with time zones. And you usually want to just get the time zone from the user and be a little careful about that. So we've got a lot of flexibility here. Sometimes you want to store them together, sometimes you don't. It really just depends on what we're doing. And I just want to check in to see if folks have any questions around date and time, because that one I think can be particularly tricky. Cool. And then the last one here is a Boolean field, which I think is a bit more self-explanatory. And we've got true and false. Note that Postgres will accept a bunch of different string representations for true. If I feed any of these into Postgres, it'll evaluate them to true, and it will evaluate all of these to false. Null, I believe, is neither true nor false. You shouldn't really rely on this. I would try to make sure, like in the code, that you're explicitly setting true and false. Just to keep it simple. And we can see some examples here of inserting true false values. And again, maybe for our workout, the user can have some sort of goal that they want to track. And tomorrow we'll learn about being able to set this by default, say to be false when I create a new workout. So I can add Boolean fields as well. Do folks have any questions around the data types or anything you'd like me to dig into more before we move on to table relationships?
So the data type refers to each column and what each row is going to repeat information of, right?
Yeah, exactly. Exactly.
Are you able to store images as the data type?
Yes, but you don't want to. There is I think it's called like a binary data type. Yeah, a binary data type. It gets a little messy because you have to convert the image format to the right thing. You have to keep track of what kind of image it is, if it's a PNG or not. What ends up being a bit easier is store the image as like a file on your server or on a different server. And then what you store in the database is either the path to that image file or the URL to where that image is on the server. The same way we saw like with the Poke API, it sends back those URLs that have where the image lives. There are actually Amazon has something called an S3 bucket, a storage bucket, and one of the common uses for it is as an image server where you stick your images on it, and then what we save in the database is the URL to that image. Yeah, great question. The simpler version of that is you stick the image in a directory on the server, and in Postgres we just store the file path to that. It ends up being more trouble than it's worth, I think, to stick the image directly in the database itself. Yeah, great question though, and that's one that people ask about a lot because that's a pretty common thing that folks want to do with personal projects. So that's a good one to touch on. And yeah, like you were saying, these column types specify what each column value in like every single row has to be, right? So if this was an integer and not a string, this would throw an error, right? Because this column type has to be varchar or text. And we'll talk more about constraints and relationships tomorrow, but that's one of the best things about a relational database is that I can set all these rules on like what the values of my different columns should be. And the database will enforce them because it gives me really good data integrity so that I can rely on that, like whenever I grab an exercise type, the name is always going to be, a string and it will never be empty. Yeah, great question. Other thoughts, questions around data types? Okay, awesome. We have a pretty good breakdown here in the curriculum that I kind of have on the left here, on the right here. I do recommend pulling this up and having it out as a reference. And these are the ones by far that you're going to use the most. And again, I recommend like set a data type, but keep it simple. I do recommend spending some time with the docs, mainly as you're like using data types for the first time, or like if you wanted to use the money type for your personal project because you wanted to deal with money, then I would definitely take the time to read this through. Data types can get surprisingly tricky once we get past the sort of more introductory tutorial scenarios. And as you can see, there's a whole lot of complexity here that Postgres allows for with data types. You can create an enumerated type where mood has to be one of these strings, which is pretty cool. As we'll see when we get to Django, there are ways for us to do this at a higher level in the Python code where we don't have to do this directly. But there's a lot of power in the data types, and the devil's sort of in the details. Like it's worth a little time reading about the date time types here, for example. As date and time are kind of just notoriously tricky. Um, Date and time and interval also let us do some very useful things. Like the interval type, I can convert to like years, months, days, hours, minutes, seconds. Um, Postgres has a ton of functions for working with date and time as well. So once you get something in as a date or time type, you can do tons of manipulation to it. More so as you go is when I would refer to the Postgres docs. Also, these are good docs. Like they are pretty comprehensive, which can be a bit overwhelming, but they're well laid out and they're sensible and they're not, some docs are kind of like it's really hard to follow along. These are not that. So also I think this is just really good practice for reading docs is with the Postgres docs. All right, let's talk about relationships, which is the really cool part. So there's a couple kinds of relationships that we have to think about. One-to-one, one-to-many, or many-to-one, depending on which way the relationship goes, and many-to-many. And these are relationships between our tables. Right? And I'm going to build out a couple scenarios here, and let's pretend we're building an app for dealing with flights. So we've got passengers, and a passenger has to have passport, and a passenger has luggage, and a passenger goes on flight. And let me draw a couple boxes here for each of these things, and we can play around, and then we'll put it in draw SQL. So a passenger and a passport. Not a trick question. What kind of relationship do you think we have between a passenger and their passport? One-to-one.
One-to-one.
Sorry?
No, I just said one-to-one
Yeah, why one-to-one?
because for every passenger, there should only be one type of passport.
Yeah, exactly. Exactly. Like you don't see tons of one-to-one relationships, but they crop up when you're data modeling. And the key is when there's a unique relationship, right? A passport has to belong to one person, and I only can have one passport, right?
Well,
Same with driver's license, same with an email address.
but you can have more than one passport. I have a standard passport. I have a diplomatic passport. I have three passports,
You
and
know
they're
what?
all and they
You
all
are
have
right.
slightly different data structures,
Yep,
and they're all acceptable at any
yep.
airport.
That's a really good point, Tim. Um, this is a great example of where, as the term is, like real world domain knowledge is important. I was very much thinking of this like at a much simpler level. But you're totally right. And in fact, I guess if I live, man, I should know this, shouldn't I? Would I, if I have dual citizenship, would I then have multiple passports?
Yes,
Yeah. What about US passport? Are we nailing it down to one then?
I have a standard passport, and I also have a diplomatic passport. They're both U.S. passports.
Got it. Okay. How about US standard passport?
How about U.S. origin passport?
Love it. This is a great example, by the way, of like why like thinking about data at a high conceptual level is important. Like I was not even thinking about any of that with passports. I was just like, oh, this is a great example. Like with a driver's license or something. But even with that, you know, there could be a different driver's license if you're to drive a truck or for other things. The real world is messy, and as we're designing programs and data models, there's almost always some level of abstraction that we have to bake in. If we were building a real thing, then this indeed, we probably wouldn't want this to be one-to-one. We'd want it to be one-to-many, and we'd specify the different kinds of passports. For learning purposes, and thank you for your help with this, Tim, I'm making this specific enough so that we can keep it a one-to-one relationship. But that is an excellent point, and I love it because that's like real world data modeling in action, right? Because if we were to make this real, we actually have to do this. And you know, then we have to talk about passport types. And then we might have to add some other rules to make sure that I don't have like 2 US standard passports. Yeah, Tim, that was awesome. Thank you. And actually, do folks have any questions around sort of the passport data modeling discussion? That was a good one. Awesome. And again, I'm keeping it one-to-one just purely for learning purposes. But that's a great point of how like we would have to make a design decision of do we want different tables for different kinds of passports? Do we want them all in one table with a type? There's probably a couple different ways to do that, though I would imagine one table with different types is the way to go.
I would imagine you would probably be using an API to verify or validate a passport in this app. And
Possibly. So
so you
that outside. Oh, go ahead.
so maybe to take that not that information, you'd know what the API needed, and that would be the one-to-one ratio, relationship, like the passport number with the name.
Uh, yeah, that actually wouldn't affect. Some of that is outside the scope of the data model, but you're absolutely right. We would need this. We'd need the number. We'd need the name. Do we need a passport type if we have a passport number?
The number should tell you what the type and the country is.
Right. So that raises a good point of because maybe for the purposes of our program, we do want to know the type and the country. But then the way we have to do it is we have to use the passport number to fill this stuff out. Or maybe we decide, you know what, I don't want to store this in the database. I want to get it from the number. But the trade-off here is then every time I want to know the type and country for this passport, I have to call an API. So we might in fact want that there so that we can save that. And then we just have to trust that we've gotten the data incorrectly, which is outside the scope of the data model, but a really good example of some of the trade-offs we would make in thinking about design. But does that also help illustrate how? Yeah, it's tricky, right? Because as you pointed out, if we want like really strong sort of data integrity and normalization, I actually don't want type and country here because I can get that from the passport number using an API. But the trade-off then is I have to make an API call every time I want that information about this passport. And I am going to switch this back to a one-to-one just for teaching purposes.
Sorry to go on a sidetrack there.
No, I love it. I hope I didn't sidetrack folks too much on that. I actually love those discussions, and that's actually a really good example of like in an interview, like being able to talk about the different trade-offs between the different approaches is kind of more important than figuring out the quote unquote best approach, right? Because best is going to depend on what our goals are. but being able to kind of talk about different ways to skin the cat and what the trade-offs are is really where we can show our value as engineers. So we've got this one-to-one relationship between a passenger and a US standard passport, which we've simplified for the purposes of learning. How about like a passenger and their luggage, which I'll represent with a circle? What kind of relationship do we think is going on here?
One to many,
Yeah,
possibly.
right, exactly. Depending on what do we call luggage, and let's call it, in fact, luggage item. Speaking of the importance of naming things, is it a suitcase? Is it a backpack? Is it a snowboard? It could be anything. It's a luggage item.
It's a checked item.
Yeah, I like it.
Well, I guess if you're considering carry-ons luggage as well, then luggage item is probably good.
Right. Well, and that's a good point. Like, have we checked in yet? Have we not? Depending on what we're building the software for. But you're probably right that checked item is what we'd want to use as the name if we were doing it. And so here I've got a one-to-many relationship, right? Where my one passenger can have many items of luggage. And actually, let's go ahead and let's grab this and we'll put it over there. And we can build this out a little bit as we go. And we can kind of see some of these relationships. Our passenger, let's say, has a passport ID, and we're going to connect that over here to the passport ID. And that's going to be a unique one-to-one relationship if I can just get. Oh. And here, well, I can't really, what's the problem of if on the passenger I stick like a luggage item ID column?
You're one to many, so they're gonna have multiple IDs.
Exactly. So where do what do I need to do instead? Well, I gotta stick a passenger ID on this luggage item over here. Right. So for one to many, depending on which way the relationship goes, that determines where we stick the foreign key ID. And the way that I remember it is like a passenger can have many luggage items, but a luggage item has one passenger, and that helps me kind of remember what goes where. And then finally, we've got flights. And so what's the relationship between a passenger and a flight?
One to many, potentially.
What?
Many to many?
Yeah, many to many, I'm thinking.
I mean, it could be either, I guess.
Well, right. So if I say one to many, a flight has many passengers, but a passenger can only take one flight, then that's a little limiting, right? You know, what if I have a layover? Which I think all of you kind of recognized and inferred because every single person who said, you know, one to many put some sort of caveat after that. And that's a good sign here that we've got a many-to-many relationship, right? Where as a passenger, I might have a flight to London and then to Spain. And on the flight, there's dozens of passengers. So this is a true many-to-many relationship. And many-to-many relationships get a little trickier to model because I can't just stick a passenger ID column on here like I did here with the luggage. So anyone know sort of like the standard technique for dealing with many-to-many relationships? I figured some folks might have seen it, but we haven't covered it yet, so there's no reason that you would. And the answer here is we actually need to make a new table, and we're going to call it passenger flights. And this is what's called a join table. We'll learn about join queries later. It's a way of combining different tables so I can see all the passengers on a certain flight. And our passenger flight table is going to have its own ID. And it's going to have a flight ID column. And it's going to have a passenger ID column. Now the flight ID in the real world should probably be unique. Because I think flight numbers are unique, but we're not going to worry about that too much.
They're unique for the day. They recycle every day.
Oh, I did not know that.
Yeah, the same flight from the same place to the same other destination from departure on the same time will always have the same flight number.
Got it. Okay, that is very good to know. And I think then we want, let's see, passenger flight. I want to say this is one-to-one. I always get a little, yeah, that should probably be one-to-one. And then this goes to passenger ID. And actually, no, a passenger can be on many flights. And a flight can have many passengers. So this is in fact many to many going in both directions, which I always find a little confusing. And like to kind of draw it out here because I find this helpful. I'm going to do it real simple. Let's just say we've got a passenger table and a flight table. And now we've got what's called our passenger flight join table. And I really shouldn't have included the names in the table, but that's okay. And here, I think you all can see why this is called a join table, because each row here in this table represents one instance of that many-to-many relationship. You all see what I'm saying? So this join table technique is how we deal with many-to-many relationships, where I've got a totally separate table and it's got all my foreign keys that I care about, though it's got its own primary key, and each row represents a passenger on a flight. And this is a super common pattern that you will see everywhere. So this is probably the most important takeaway from today, because you absolutely will need to do this to model many-to-many relationships.
So to be clear, for the two things that you're trying to connect together, you give them the ID of the join table. Is that correct?
You don't give them the ID of the join table. You connect each one to its own foreign key, like here for flights. That connects over here to flight ID, which is a foreign key on this passenger flight table. And then passenger ID connects over here to the passenger ID. This primary key here is more for like lookup purposes. Like there's not a lot in this example, but there might be more. It's also just, if you kind of stick a primary key on everything, it ends up making life easier. If I want to get all the passengers on a flight, it's nice to be able to say, get like the IDs of all these rows, if maybe I need to do something with them or manipulate them somehow. So the primary key here isn't actually doing any work in the many-to-many relationship. That's more for us to just be able to leverage this down the line with other queries. It's these two foreign keys here that are doing all the heavy lifting of the many-many to relationship. Does that help answer your question?
Somewhat, but I'm still unsure how you are defining the relationship, because at least on the flight and passenger table, it's, and at least the way I consider it, it's giving its ID, but it doesn't feel like it's receiving anything. I'm still struggling to understand this.
Yeah, I mean, I think you're basically right, because if we look at this flight table, and I'm only doing flight 4, I'm saying flight 4 has passenger 1 and passenger 2. And that's all happening right here, right? And we're not actually doing anything with this. So what I'm doing when I'm creating these tables is this passenger flight table, this join table. I'm telling the database this flight ID column. Well, this is a foreign key that's going to point to a flight. And this passenger ID column, this is going to point to a passenger. And as I get more passengers for my flight, and maybe a passenger is going on a connecting flight, and we've got another passenger on the flight, and so on. Each row here gives me, and I wouldn't overthink the part about sort of what is the relational database doing. I think thinking of it just as a plain old like spreadsheet and like a table is the way to go, because that's really what it is at the end of the day. Is if I need a table to see all the passengers like on a flight, what I really want is I want like a list of flight IDs so I can see all the different flights, and then the passenger ID for each of those. And this way, each row uniquely identifies a specific passenger on a specific flight.
That helps it make a little bit more sense.
Yeah, and I think this one is the one that will take a little bit of time. We do have some examples here as well that I think are worth looking at. We've got like pets, where you can see a pet store, where take a look at this transaction pets table. If you folks take a look at this, like if I'm buying a pet from the pet store, it's like a receipt, right? The pet ID and the transaction ID, because the transaction has the customer information and how much I paid. And if I want to keep a track of, like, say, maybe we could put the pets here, but this is a many-to-many relationship where I can see like what pets were with what transactions. Another example here is cars and owners. And I think this is a good one, because like Tim, like you pointed out with passports, like I might have like a truck and a Jeep and a motorcycle and a car for the winter. So one owner could have a bunch of different cars. Well, how do I represent that? I need a separate table, and one column in that table is going to be the car ID, and the other is going to be the owner ID. And this again is what's called a join table to represent this. In this case, I guess we actually don't need this because you could put an owner here. But if we want to imagine that we're like selling cars and stuff like that, like maybe we don't want the owner on the cars table. Because a car can't have multiple owners, but an owner can have multiple cars. So this makes it a bit simpler. So this isn't maybe a true many-to-many relationship. Though I guess it is many-to-many, because if I sell you my car, well, then the car has had multiple owners, and how do I keep track of that over time? And maybe I do that with this car owners table, and then there's a date column. And so if I want to see the history of who's owned a car, I can go over here to car owners, and I can see who's owned it over time as it's been bought and sold.
So maybe not selling cars, but keeping track of state registrations for cars, where you'd keep track of all the different owners that car had had in its history.
Yeah, it's a great example. Yeah, I agree. That's a much better way of thinking about it, of like state registration for cars. The last scenario here that you can see is a school management system. I know I ran a bit long here, so let's take a break. And I think what I want to do is give you all 30 minutes to work on a design problem. So let me show it to you all quickly, and then we can take 30 minutes. And then when we reconvene, we'll start getting our hands on SQL. Sound good? Okay, awesome. So the assignment is here. We just wrote it out. There's not actually a repo for this one. This one is a bit open-ended. We'd like you to come up with the design for a game store. Feel free to start with TL Draw and Excel spreadsheets, but I do think you should end up using Draw SQL because it does force you to think about column types and stuff like that. So even if you don't start your design here, I'd like you all to end it here. So if you look, it's a little hidden, but if you look here in example and data for today's lesson, we can see some CSV files. When we come back after you all have worked on this for a bit, we'll actually see how to import all this stuff and run the SQL to work with it. But you can see here like information about action figures. So as you're designing your action figure table, you should take this into account to figure out your column names and types, right? And you can see there's employees, they've got salaries, there's games with prices, and there's posters. So basically there's like 3 kinds of products: posters, games, and action figures. And then we have employees. Employees, you might not need to do too much with them right now, but just think about like building a data model to represent that CSV data that's there. And if you want a stretch goal, maybe think about like logging purchases. How would you do that? You know, maybe we want to track which employee handled which purchase. That might be a good sort of follow-up step once you've built a basic data model for these things. Does that sound good? And do folks have any questions? Okay, cool. This one is a bit more open-ended. Take 30, take a short break, dive on in. I would start just by modeling the CSV data that's there. And then you can start thinking about maybe how do I want to model a transaction. And then when we come back, we will actually start writing some SQL to create tables and dive a bit more into psql and how to use it. Thank you very much, folks, and I'll see you all in 30. Let me go ahead and... All right, let's pick up where we left off. There was a couple of questions and a good discussion that I'll dive into. Also, just to recap, like we talked a lot about schema design and practiced a couple. And now we're gonna dive in and get our hands dirty with psql and Postgres and talk about the difference between the two. Jason, you had a really good question of how do I model like a many-to-many relationship. And let me just pull up one of the examples that we were looking at before. In fact, let's go back to our workout example because we didn't get to add this in because I didn't want to open this door yet. But if you all remember, we had a user, we had a workout, we had an exercise type like push-ups or sit-ups or what have you. And then the idea was there might be a bunch of different sets in a workout, like a set of like, 10 push-ups, and then a set of 10 sit-ups, or maybe I do 2 sets of 10 push-ups. So somehow I want this many-to-many relationship that I keep, having these two things butt heads with, because I want a workout to have multiple sets. And I guess, well, I apologize, because I guess, so let's also say for the sake of argument, I want to be able to save my sets and design my workouts. And so like my set of like 10 push-ups, I want to be able to reuse when I'm designing workouts. So I'm kind of creating a feature need for not only a workout to have multiple sets, but a set to be used in multiple workouts. Does that make sense to folks? And Jason, are you tracking with kind of what I'm throwing in there as the feature add? Okay, awesome. Because without that, we could probably just the sets add a column saying like workout ID and call it a day. Because that lets us have a one-to-many perfectly fine. Right? But as to your point of how do we do a many-to-many?
Yeah, that's what I mean. Those 3 options don't allow you to.
Right. And so we saw this right before the break, but this is where we need to create a join table. So I need to actually create a separate table here so I can like have pre-saved sets so that not only can one workout have many sets, but one of my pre-saved sets can be used in many workouts. And a join table has a minimum of 3 things. Its own primary key ID that's there mainly for reference, and in the future we'll see where there's some value to it. And then it has 2 foreign keys of each of the tables we are connecting together. And then what happens here is one row from here uniquely identifies a combination of a workout and a set. But this is how I can connect workouts and sets to have a many-to-many relationship. And if I was to hop back to the spreadsheet, it would look like this. Where now each row uniquely identifies, hey, set number 2 was used in workout number 2. You know what? Set number 3 was also used in workout number 2. Set number 1 was used in both of these different workouts. And we kind of saw that as well with the passenger flight example, where one passenger can be on many flights and a flight can have many passengers, where we have a join table with the flight ID and a passenger ID. Does that help answer your question, Jason? Awesome. Yeah. And again, this is a bit more of a complex technique. I think drawing it out a bit to begin with can be useful. And we do have to create an additional table to do it and to implement it. And the pattern is called a join table because when we learn about queries and using a join query, we use this a lot. So this is kind of the standard pattern for many-to-many relationships. And actually, on that note, let me just dive in and let's talk about our game store a bit, and then we can talk about some Postgres and psql and write some code. So let me put this over here, and let me go back and let me pull up our game store code, if you'll give me just a sec to paste it in. So the design assignment was we've got this different data. We've got action figures, we've got games, basically things that we can purchase. We've got posters, and then we've got employees, and they're not really connected right now. And that's okay. But I can see here like an action figure is going to have a title, a quantity, a price. I can see here a game has a title, a quantity, a price. I see here a poster has a title, a quantity, a price, and then same with employees. And so if we're building this out, and I might just build out the employee just to keep it simple, because I do want to get to writing code. As I'm building this out, I need to think about things like employee names, if I want it to be able to be null or not, which I don't want the employee name to be null, that we have to have an employee name. An employee position. And in fact, this one might be a good one. Maybe I do want to make a separate table for position. This adds a little complexity, but it just for sort of learning purposes, I think is kind of cool. So a position will have a name, and it will be a varchar, and we'll put it over here. Now, to do this requires some extra work when I'm actually importing the data, because I've just created a new table and I'm actually modifying the
For me, I was trying to do like categories, because there's overlap, between the three different tables of posters, action figures, and games, where I was
Right.
trying to join tables with categories.
Right. Right. We could totally do that as well. That it gets a little trickier. I think the way this data has been designed, it might be a bit tough. Even here, like when I write SQL, I don't think I'm going to implement this because it just requires an extra step that I don't want to go through at the moment. You're absolutely right. Like if we look at posters, games, and action figures, we see there's quantity and price. But the tricky part then becomes like, these columns have a different title, and how do I make a separate table? Like if I want everything, I could absolutely could have categories, but then it's a little tricky. What do I connect it to? And I almost end up doing some meta programming, right? Because I have to like figure out a way to stick in the table name. And Jason, what we'll see is that like the answer to that is actually in the Python code that would be interacting with our database. Really, the question would be like before we import all this data, if we wanted to maybe manipulate it so it's just like, and maybe this is what you're saying, like maybe I want one product table, and the product has a title and it has a category and it has a quantity And maybe we should in fact call this like product inventory, but I'll worry about that later. And it has a price. And really this is like a price per item. And then we would have to add, like a product category table that has an ID and a name. I don't know if that's the road that you were going down, Jason.
Yeah, more or less. I mean, there was overlap, between the categories because I could find real life. I basically did real life, fantasy, and
Yeah.
gen essentially. I was trying to do.
Oh, I see. With sci, not okay. I was thinking like action figures, games, so on. I see what you're saying.
Yeah.
Yeah, yeah. No, there's a lot of ways to slice and dice it. And in fact, that could even be like an additional, like, that could be another one in addition to like product, whatever
Yeah.
we're naming it. Yeah.
Actually, I think the way you're doing the products might keep it more simple than what I was trying to do.
Well, we could do like genre ID, just to use a different word than category. Um, if we wanted to really like go to town here. And then we have we'll have to call this genre. Um, and then the genre needs a name. And that's gonna be a varchar. And then we would have again, and this would probably be a many to one. Um, unless we wanted a product to belong to multiple genres, which would make it more complicated. And then in fact, we would need a join table for a many to many relationship. So this is actually a pretty cool way to do this data model. But as we can see, if we do this, we actually then need to add a whole bunch of intermediate steps before we import the CSV code, right? Because we have to import it and we kind of have to manipulate it so we can feed it into the database the right way because our products are broken up among these different tables. So again, there's a lot of different ways to skin the cat here, and the goal here is really to just give you all a chance to play around with design and start thinking about stuff.
Why did you put in your product you went one to many for genre ID?
Someone's volume might be super low.
Sorry, yeah, my mic was up in my head. Why did you do that? You went product genre ID one to many instead of genre one to many to genre ID.
Oh, I think that's just a mistake on my part.
It's because I think you started by drawing a line from genre ID to genre instead of the other way around. Okay, that makes sense.
Yeah, and in fact, this should be this way as well. I always get confused with that. You're absolutely correct. Yeah, thank you, Tim. And do folks have any questions actually about sort of this data model that we've been putting together, whether it's like a particular part of it or how we would implement it or a part that might be worth digging into a bit more?
This is all basically nested objects, right? And as you go down the tree, you go from one to or from many to one because you have like
Yeah.
product is an object and then it has a key value pair of say category which goes to product category. So you
I
could do
think
product ID dot name.
um I wouldn't think of it as nested objects. Um I named this product category because you're correct, there's a relationship there, and I wanted the name to represent that. But I would really think of this as like tables because this is how the data lives. This is sort of the fundamental, right? If in Python objects is our building block, like tables, columns, and rows are conceptual building blocks for SQL and Postgres. Um, Now Postgres does give us some fanciness, and we'll see in a week with Django, it gives us some OOP fanciness. But fundamentally, relational databases are about tables, rows, and columns, and the relationships between them. Does that make sense?
It does.
Yeah, that's a great question. And it does get fuzzy because we will indeed throw OOP back into the mix. But, if like sort of the conceptual building block of React is like a function that renders something to the DOM, and then like a class and an object is sort of the conceptual building block of Python OOP for relational databases, it's definitely tables, columns, and rows. And that's the way to think about it. And yes, we can have relationships between them, but they're still tables and columns and rows. I think the one thing I'll point out here is having like the quantity on the products table is fine, and it's in a lot of ways pragmatic, but in some ways it would make sense to have like a product inventory table instead, right? That like this maybe had an ID and a product ID and a quantity. Or maybe we even have a separate row for each individual product item, depending on how granularly we want to track stuff. But this also works and it's pragmatic. So as with all things, there's more than one right way to do it. But this is a pretty good example of like some flavor we can throw into the mix with our data modeling. All right, let me switch gears. I realize, I apologize, we're a little tight on time. I might steal a little bit of time after lunch, but let's look at writing some code. So let me talk just very briefly about Postgres and psql. And to kind of remind us, and can everyone see my VS Code and read everything in the terminal? Okay. Okay, awesome. So there's two things we're using. We're the Postgres database engine and psql, that's called a client. And sort of as you can see here on this little diagram I made, psql's job when we run it is to talk to the Postgres database engine. And Postgres could have a bunch of different databases inside of it. For most of what we'll do in the class, the Postgres server or the Postgres engine is going to be running on our own computer, but it doesn't necessarily have to be. And unlike psql, Postgres is running in the background. When we start up our computer, it runs as what's called a daemon. You'll often see it called like a service, which is something running in the background and something that the system starts for us. Most background services or things perpetually running also get assigned a port number. And in fact, when we run the Vite dev server, that gets a port number as well, right? And over a network, whether that network is the internal network on my computer or over the internet or any other network, ports are how the different things talk to each other. And it's like addresses. If I want to send you a letter, I need your address. If I want to send you an HTTP request, well, I need your host name and your port. Postgres is by default runs on port 5432, and that's usually the port you see it on running everywhere. And the job of our psql client program is to be able to talk to Postgres. So, way back in install fest, we all set up psql. We can run that command and psql runs. There's a good deal more going on under the hood there. And just to give an example of this, let me grab something to copy and paste. So when I run that psql command, what I'm actually running is this command here, where what we see is within the quotes, a URL. It just looks different than the ones that we're used to seeing in the browser. Because rather than the hypertext transfer protocol that's secure, HTTPS, we're using a different URL scheme specific to Postgres. Notice we still have the colon and the 2 slashes. Here we've got my username, a colon. If I had a password set up, it would go there. After the @ symbol is the host name. localhost, meaning I'm connecting to the Postgres running on my own computer, the port that it's running on, and then the name of the Postgres database, which we all created a database with our own username on day one of InstallFest. I also created a little earlier today a database named foo. And when I run that command, psql connects to the Postgres server and to that database. Now, if I wanted to connect to a Postgres server somewhere else at some different IP address, it might look like this. And I'm just making up this IP address. I'm not even sure if that's a valid IP. And the password might be here, and then the database name would be whatever the database is. And this will fail because that URL, that IP address doesn't exist. And I don't think I want to wait for Postgres to figure out that it doesn't work. We've also seen this same command run a slightly different way, where on the command line, we've got psql, and then we have a bunch of flags, -h for localhost, -U for username, -d for database name, and -p for port. Now, the good news is by default, Postgres, if I don't give it any arguments, will connect to localhost on port 5432, and it'll look for a database with the same name as my Linux username and use that as also the name to log in with. So because we set up databases with the same names as our Linux usernames on day one, I can just type psql and connect. So this is not like of immediate importance, but I do think it's really helpful context to see, to get what psql is and what Postgres is and what each one isn't. So I just want to check in and see what thoughts people have and what questions y'all have around this. And how are we feeling about this? Pretty good? Okay, awesome. And I have some good news here. It's linked into the curriculum, but we have a pretty awesome cheat sheet that has pretty much everything you'll need to do with psql and Postgres. And this is good because psql on the command line is a little funky, right? I have to use this / and all these commands. L will give me all the different databases. C will connect me. And if I look through here, there should be a game store database that I was playing with earlier. And indeed there is. And C will connect me to the game store database. And if I do /DT, there are no tables in the game store database. If I want to delete my game store database, I can do that and put a semicolon at the end. I don't need to type SQL commands uppercase. That's just a convention for readability. It won't let me drop a database I'm connected to. So let's connect to my database. Let's drop the game store database, which is now dropped. Let's create it again. And let's go over how to put stuff in it. Because this can be a little tricky. So we're going to use a couple different commands here. And I've kind of copied over stuff so we can see it and work with it. So all of this is in the examples directory from today's lesson. Let me just kind of walk you guys through what we've got. So first off, of paramount importance is once we are moving stuff into Postgres, like CSV files and running SQL, it matters where we run psql from. So just get in the habit of running psql from the same sort of your project root directory. So you can use simple relative paths for your SQL files and data. And I have two terminals open here. So I can have psql open in one and the command line in the other. And let's take a look at this SQL. And in the interest of time, I haven't written it all out, but let's walk through what it's doing for a part of it. And then we'll run it. And actually, before I dive into this, let me just pause and see if folks have any questions thus far as I'm sort of doing this overview of psql and Postgres. Okay, awesome. And I do apologize. We're going to run a little long, but we should be able to wrap up soon. Is everyone okay with that? Okay, thank you. So a lot of these commands are pretty straightforward. Drop means delete. If I don't add that if exists, I get this annoying error. I can ignore it in both cases, but here the error doesn't like stop the SQL from running. And I'm going to be typing out some SQL in here to run it bit by bit, and then we'll run the whole file. And this is nice to do because what we're going to see in a minute is that the flow is I modify the SQL file and then I keep running it. It's a pain to write SQL in psql. I don't recommend it. Queries is okay. This stuff less so. From the perspective of psql, the semicolon is what ends a line. This is a comment right here, these two slashes. I create a table like this. I give it the name, and then inside the parentheses, each of the columns. psql's fine with this. It doesn't consider, it's not going to run any of this until it sees a semicolon. Now it's created a table. And now I can actually see, oh, those are the other. I thought I dropped this table and deleted all that stuff. Let's just drop table examples, drop table items, drop table, drop table order items. The cascade we'll talk about later. And now we have just that one table that we created. And I should also now be able to do /d game. And that gives me information about the table that I created, and we can see the different columns. And we can see the types. We can see the not null rule that was set on the ID because this is a primary key. Postgres makes it not null for us. I should probably, in fact, add not null here. So I actually want to alter table. I want to alter the game table, and I can use the alter table command to do this. And then I want to add a constraint, which we'll talk about more tomorrow, but it's a rule on a particular column. And we're going to alter the column game title and set to not null. So we will not allow null values into the title column. And if I look at that, I can see that I've now added that constraint. You can use alter table to get rid of columns. And do all sorts of things. I'm in fact now just going to drop table game entirely, and I'm going to reconstruct it because I've been playing around with it. And now we've got that table back. So yes, you can do this in psql. It's not very friendly. It's much better to write the SQL. And this is kind of the pattern you'll see where you start with drop table if exists, create table game, and this will actually then copy all that SQL from that data file. And we have to use this CSV header command to tell Postgres that the first row of the CSV data has headers. And in fact, let's just run this individual line. And we see copy 10 that tells us that this was successful. And now if I do select star from game, we see our data in there. Now, this is where the relative paths are important, because if you all remember back here on the terminal, I made sure to run psql from this directory. So the relative path /data that I used in that copy statement is correct. So that's kind of the key thing here, is making sure you're running psql. Like I would just run it from your project root directory and have everything be relative off of that. And I just want to check in and see if folks have questions thus far, or things that might be good to go over a bit more. So how are we feeling about this? Awesome. So let's check out all of this SQL, and then we'll run the whole thing. I'll show you 2 ways to do it, and I'll show you what the workflow looks like. So you can see the pattern here is pretty straightforward. Drop table if exists, create table, and we add our rules, and then we import the sample data. And then we're going to do this for all of the different CSV files. So we would have to do some more manipulation if we wanted a more complex data model, but I think it's better to start simple and go from there. So there's 2 ways to then run this SQL file. One is from psql itself. We can do /i, and in fact, it's the command right here to run an SQL file from psql. We have to make sure we're on the current database that we want to be. So if I do a quick describe, I can make sure I'm on the game database. And then I have to give it the path to the file. So it's going to be /store.sql. And just to double check, I'll go there. And note, by the way, this store SQL file, all these copy statements are also relative paths. So I need to make sure the store.sql file is where it should be relative to the data directory, that they're both at the same level. And now if I run this, we see all of our tables got created. So this is awesome, right? But, I want to make a change to the data model. I actually do want to add like a not null constraint. So I'm going to add that here if I can remember how to do it the right way. And I think that should be it. So this is where having the drop table, if exists, is useful, because I can run the whole command again to rebuild the whole database. And it looks like I probably made a simple mistake here in adding a not null constraint. And in fact, I think the way we have to do it is I can't do it when I create the table. I have to create the table first, and then I can say alter table game. I think there is a way to add it on there, but I'm not sure. But this is good to see as well. Alter table game. Let's see, alter column game title set not null. And putting it on separate lines is really a little bit of dealer's choice. I think this is not too bad for readability. And now let's run this again. And that seems to work just fine. And now if I look at the game table, I've got my not null constraint. I've got everything I want in here. So this is why it's nice putting all of the SQL you want to run in a file. It gives you a really nice, easy workflow. And I just want to pause and check in and see if folks have any questions around that.
So that's a for sure. You can't add constraints when you create the table. You have to do it later.
Postgres add constraint in table creation. I probably just got the syntax wrong there. Let me double check and get back to you on that one. I'm not certain. I want to say yes, but let me just double check. The one thing that is good to think about with adding constraints, though, is sometimes, depending on what your data looks like, you might want to wait to add them later until the data is cleaned up and organized. So I want to show two things real quick. I want to show how to run an SQL file from the command line. So if we wanted to run that same SQL from the command line, we could do psql. I think it's game store is the name of the database. And in fact, let's drop db game store. Maybe is it drop database?
You said DROB by mistake.
Oh, thank you so much. So these command line commands, I'm not on psql right now. These are just shortcuts to do the same SQL that we saw before. So I dropped it. I'm going to recreate it. And now let's do psql game store ./store.sql. And let's see here, role store. I think I might need to add a couple other things here. My apologies. We need to tell psql what database and what user, and that we're passing it a file path. And now that should work for us. And if I do psql connect to game store, then we're in. And if I examine the tables, we see that we've got all that stuff back. And so the last thing I think I want to show folks is, let's say we want to add some new data in here to, let's say, the action figures table. So this looks relatively straightforward. And there's a couple different ways to insert in SQL. I kind of like doing it this way. First, we give the column names, and we don't pass ID, because that's a primary key that Postgres will take care of us. So we say, hey, for action figure, quantity, and price. And I haven't added a semicolon, so this SQL is not run yet. I'm still building it. we're going to pass in the values of, anime character figure 5, quantity 40, price $12.99. And I didn't add a semicolon at the end of this, so I think this whole thing. Let's try this one more time. My apologies. I forgot. This is the most common mistake to make, by the way, in psql, is forgetting the semicolon. And that's actually what I expected to see. So we get this interesting error. Null value in column ID violates not null constraint, failing null constraints. But, I thought that Postgres would take care of the primary key for us because it's auto incrementing. So what's going on here? And the answer is that because we imported all of this data, like Postgres didn't do what it needed to for creating IDs to sort of get this serial value going. So we do have to run a command that is going to create, I believe, a sequence that Postgres will use to generate the ID. And if we sort of we can kind of see this, in fact. So when we look at the action figure table, we see the columns, the column types, some constraints. We see an index for quick lookup was created on the primary key. What we should also see is something called a sequence for the auto incrementing. But I believe it's because we kind of imported all this CSV data that already had primary key values. And so I'm pulling this command straight from today's curriculum. This is, you won't always have to do this, but it's good to know if you're running into this error. We're going to run this command here that is going to create a sequence, which is what Postgres uses for these auto incrementing keys. And we're going to set the sequence to be whatever the highest value is already. And if you all see that select max ID from action figure, that's what's going to, this sort of like subquery command, do that work for us. And let me make this a bit bigger so we can see it. So this is a little more like in depth than we need to get. Like it's not, let's see, and I'm not sure that ran. Let's try running this one more time. In fact, I think I'm missing a closing. Yeah, I'm missing a closing parentheses at the end. So this is very much a copy and paste command. What's happening here is we have a subquery that's getting the max current ID value, and then using that to set the value for our auto incrementing sequence. And let's just fix that real quick.
Where's those action ID sequence? Is that the column of what you're trying to have Postgres continue making a new number for?
Oh, yeah, I see what you're saying. I do have a typo here. This should be action figure ID sequence. Tim, as you pointed out earlier, there is some name spacing, so there may be another issue here, but that was definitely a typo on my end. Let's see here. Relation does not exist, so that's okay. I would have thought, to be honest, I'm a little unclear why the sequence didn't get created when we specified this as the primary key. What I may just do here is an alter table to turn it into a primary key type. And I think that will solve it for us. So,
Where did you get action figure ID sequence?
oh yeah, so action figure is the name of the table.
Mhm.
And then ID sequence that's Postgres's naming convention for sequences. So that one, it has a little bit of magic going on. So let's try. That is
Oh,
hard.
So ID sequence refers to I forget what the proper term, the secondary table that keeps track of the IDs.
Sort of. We haven't really talked a lot about sequences, and it refers to something that also doesn't exist yet. So um so it is a little confusing right now. Let me see if I can modify this ID column to be a serial primary key. And yeah, I may have to come back to this one, folks, because there's a new way to do this in Postgres. And I think we're missing a step on this as well. My apologies. I think yeah, because there's a couple things going on here because we want to get this set as an auto incrementing key. But we also want to use the existing IDs. So there may be an easier fix here than what I'm trying to show us. Because let's see here. And we're also running a bit long. Okay. So there's a couple of things going on here. It looks like this did not get set as the primary key. Alter column ID set primary key. So let me let me come back to this one because it's going to be a relatively short set of commands, but I think there's just something that's happening here with the interaction that I'm not tracking the right way. And I don't want to try, and I think I've already kind of painted myself into a corner here debugging it live. Normally when we do this, like setting in primary key, that should take care of it, and we should see it here. And we do see primary key here, in fact. This also might be a Postgres like version issue. Because sometimes you'll see like serial primary key set on things. So let me debug this one offline and get back to you all. I apologize. That was the last thing I wanted to show people, but I think it'll be easier to just get it working and then share the code. For us, the main thing here is just to recap. And let me go ahead to and open up. There we go. To open up our Explorer here. So just to kind of recap what we walked through here, the main thing is when you're running psql, make sure you're running it from your project root directory. And then you're going to want to write and like modify your SQL as you go. And in fact, we can add serial primary key here, and we can add it here and see how this does. And then all of these copy commands for CSV files are going to be relative paths, as will the command to run the SQL itself. And yeah, I think I have to. Let me just follow up with the right way to add our auto incrementing primary key, because I think
I pulled up the code and serial is lowercase and there's no int because I'm assuming it's like a redundant.
yeah, you're right about ints. The lowercase uppercase doesn't actually matter. That's more just convention. But that's a very good point, because serial is actually type that like under the hood uses integer. Now this might cause a different issue. So that actually does appear to work. I think you may have hit the nail here. Let's look at our action. Yeah, there we go. So yeah, okay. So there were actually two issues here. I apologize, folks. I should now actually be able to run the fix that we had, and then let me explain what the issue was, and then we can break, because I realized we did run a bit long. And Kenny, I think that was you. Thank you so much, man, because I think that was the missing bit. So let's try this one more time. And we're going to do this for the action figure table. Yeah, all right. I have to come back and follow up with the correct way to update the sequence, the ID values. But let me show you all what changed. And Kenny, thank you again. So if we look at one of these tables, like let's use the action figure one that we've been looking at. So what we had before was this, which is fine. It tells the database that this is a primary key. but we did not tell it to do any sort of auto incrementing. And if I change the column type from integer to serial, like we're pointing out, it does tell us to do some auto incrementing. And what got added and what was not there before is here under this default setting, which is the default value when I create a new row. So the default value for ID when we add something in there is it uses this action figure ID sequence and it gets the next value from it. And a sequence is, you can think of it, it's basically a counter that like generates the next value. And in fact, I wonder if the issue here is that this should be, yeah, and I think we may have done it. And now the insert works. Yeah, so I will update the curriculum, folks. My apologies about that. But we did finally succeed. You can see in here, I inserted in there anime character number 5. So a couple learnings, and I think this is me getting back in the saddle with SQL as well. Just to recap, when we're creating a primary key, we really want to do 2 things. We have the column name, the column type, and then our special constraints. And primary key is a special kind of constraint. We normally want the column type to be serial, which will set up the auto incrementing that's really nice. But if we are importing data that already has primary keys, which isn't always the case, often this is empty, and in which case that's great because Postgres will generate that for us. But if it is, we have to do an extra step. And if we use the describe table command in Postgres, we can see that a serial primary key has a default value. So every time I insert an action figure or a game, if this game ID column doesn't have a value, Postgres will generate one, basically incrementing a counter under the hood using something called a sequence. And so I did have to run that command to update the values of the sequence to match these IDs that we brought in. I realize that last bit is a little tricky and touches on stuff that we haven't gone into as much. That's more of a, it's okay for this to be a little magic. And the main thing is to, I think, be able to know how to run the command. I'll also see if I can come up with like a cleaner way of doing this. But this is good to see a little bit under the hood of what's happening with the sequence. You know, there was a really good question of where is that name coming from? And we can see here, this is just the Postgres naming convention of table name, column name, and then it sticks underscore SEQ for sequence at the end of it. And what we're doing is we're setting the value of that sequence to be the maximum value from the data that we imported. And then that allows us to insert new stuff with updated primary keys. Thank you folks for sticking around. I realize we ran a bit long. I'll send out the pairing pairs after lunch because today is a pair programming day. For today's assignments, you all have already started working on part 1 of the game store. I think it's a good thing to pair on the game store design. So the first assignment is, now that we've kind of gone through writing some SQL, and I'll push up all the code I wrote, write some SQL queries to create employees, posters, and action figures to load them in. I would recommend keeping it simple. And in fact, the code I wrote, you can find here in this directory. We then have some more open-ended schema design assignments that should be a lot of fun, where we only want you to do the first step of this one, which is designing a data model for an ice cream store. And we've given you some rules and some challenges and we want you today to work on the stage 1 tasks, and it's open-ended on purpose. So you will have to make a bunch of design decisions. And then there's another open-ended schema design assignment, except this one starts with CSV data for a pizza delivery company. And again, we want you to start just with the stage 1. So I can definitely stick around for folks that have questions. I don't want to keep people longer than I already have. Thank you again. So let me break everyone for lunch, and then I can stick around for whatever questions folks have. I'll get the video and the code pushed up soon, along with like a short TLDR of how to deal with the primary key issue when we're importing from a CSV file. So thank you.